Now we're going to talk about self-inductance. In discussing mutual inductance, we assume that one circuit acted as the source of magnetic field and that the EMF under consideration was induced in a separate independent circuit linking some of the flux created by the first circuit. But whenever a current is present in any circuit, this current sets up a magnetic field that links with itself and varies when the current varies. Hence, any circuit with a varying current has an induced EMF in it resulting from the variation of its own magnetic field. Such an EMF is called a self-induced electromotive force. As an example, suppose a circuit contains a coil with n turns of wire, as in this diagram here, and that a flux passes through each turn. In analogy to this equation here, Mn2 flux 2 over I1, this mutual inductance term, we define the self-inductance L now, equivalent to this M, of the circuit, or simply its inductance, L equals N flux over I. This relation can be written as N phi equals Li. If both flux and current I change with time, then the instantaneous change here would be N dflux by dt equals L di by dt. And since the self-induced EMF has magnitude, since it has this magnitude here, N dflux by dt, it follows that it can also be written EMF equals L di by dt, because these two are equivalent. We've now got an equation for the EMF for a single coil with a current running through it, and that describes its self-induced EMF. It follows that the self-inductance of a circuit is therefore the self-induced EMF per unit rate of change of current. The SI unit of inductance is again the Henry. A circuit or part of a circuit that has inductance is called an inductor. An inductor is represented by this symbol here. The direction of self-induced non-electrostatic field can be found from Lenz's law. We consider the cause of this field, and hence of the EMF associated with it, to be the change in current in the conductor. If the current is increasing, the direction of the induced field is opposite to that of the current. If the current is decreasing, the induced field is in the same direction as the current. Thus it is the change in current, not the current itself, that opposes the induced field. The self-inductance of a circuit depends on its size, shape, number of turns and so on. It also depends on the magnetic properties of the material enclosed by the circuit. In the last two examples, we calculated the magnetic field by assuming that the conductor was surrounded by a vacuum. If matter is present, then when we calculate the field, we must replace the magnetic permeability in a vacuum by the permeability of the material. So we're going to use this here now. If the material is diamagnetic or paramagnetic, this makes very little difference. But if the material is ferromagnetic, however, the difference is of crucial importance. An inductor wound on a soft iron core, for example, can have a Km of 5,000 and has an inductance approximately 5,000 times as great as the same core with an air core. So you can see that this Km here is tabulated for many different materials that could be used for inductors, and that's been done empirically. So to get this mu, so we can use all the same equations, instead of using mu naught, we can just use U, and all we do is we plug in this Km value, which is from the table of permeability values. So that's worth remembering. So in lots of equations, it doesn't matter if the permeability of the material is not a vacuum, as long as we just remember to look up our Km, we can just use this. Now here's an example. An air-cored toroidal solenoid of cross-sectional area A and mean radius r is closely wound with n turns of wire. We neglect the variation of B across the section, assuming its average value to be very nearly equal to the value at the centre of the cross section. The magnitude of the field, in other words going through the centre, is B, magnetic permeability in a vacuum, U naught, N, the number of turns going round, I, the current that's being put through the coil, and 2 pi r being the length, if you like, of this toroidal, obviously using r being the centre here. So 2 pi r is the length of this toroidal. Then the flux in the toroid is simply the B, which we know, given all the values, times the area. So that's the cross-sectional area here we're talking about, the cross-sectional area. So that gives us the flux through this toroidal. Since all the flux links with each turn, the self-inductance is Ln flux over the current. So we can plug in this value and get our inductance value for the L, and that we can just replace the flux up here, put it in there, and that gives us the inductance. So now we've got the inductance of this toroidal. We've worked it out. Having worked that out, we can use EMF equals L di by dt. So that's what we do first. We work out the inductance. So let's just say that n equals 100 turns, A equals 10 to the centimetres squared, or which is equivalent to 10 to the minus 3 metres squared, and R equals 0.1 metres. Then plugging them all into this equation here, we get L equals 20 microhenries. Once we've got that, that's fixed all the time for that inductor. You know, we can put a label on that inductor and we can write L equals 20 microhenries, and that's it, we're done. We never have to do that again for that particular inductor. If the current in the coil above increases uniformly from 0 to 1 amp in 0.1 seconds, find the magnitude and direction of the self-induced EMF. Well, now it's easy because we know the inductance, so they ain't going to work it out. That's a tabulated value, we've got that. So then we just use the EMF equals L di by dt. Well, di by dt, we know it's gone from 0 to 1 amp, so it's increasing, and it's increased at a rate of 0.1 seconds. So we just put 1 amp divided by 0.1 seconds, that gives us the rate of increase, and just plug those values in, and we'll find that the EMF produced in the back EMF opposing that current in that coil is in fact 2 times 10 to the minus 4 volts, or 20 millivolts. So that would be the amount of resistance to the current flow offered by the back EMF. The current is increasing, so I'll just repeat this. The current is increasing, so according to Lenz's law, the direction of the EMF is opposite to that of the current, which I've just said. In this diagram, so I've drawn another diagram here. Suppose that the inductor terminals are A and B. So that's suppose here we've got terminals A and B, and there is an increasing current from, so this is part of a circuit really, and there's an increasing current going from A down to B in the inductor. Then the induced field, this induced field En, and the EMF are in the direction from B to A. So you can see because of this, it wants to oppose that current, so we end up with an induced field going in the opposite direction. And that's like a battery, with A as the plus terminal and B as the minus terminal. So it's like, we can write, you know, VAB, like a battery. VAB equals L di by dt. So that's like a battery with a plus terminal and the minus terminal. This last bit is very useful to remember that when you're doing calculations. Remember that the L di by dt is the EMF that's opposing the current that's increasing or decreasing.